What's up, scholars? We're going to be looking at some collision experiments and some more information all about collisions for our unit on momentum and impulse. So, just a quick reminder, we're talking about conservation of momentum. In all collisions, momentum is completely conserved. Now, sometimes that might mean we need to account for 2 or 3 dimensions and multiple or millions of objects, but in general, it's always true that the total momentum before a collision is equal to the total momentum after. So we can see here we have 2 objects. Here it uses A and B, but you might use 1 and 2. Before the collision, they each have velocities. During the collision, they collide. There's equal and opposite force applied to both of them, Newton's third law. And then the objects, in this case, they happen to move apart after the collision, but in fact they could do anything. So just want to remind you, conceptually, the way we would do that is we'd take the momentum of the first object plus the momentum of the second object. That's the total before. That would be equal to whatever the total momentum is afterwards. Now, whether they hit and stick together, hit and move in the same direction, hit and bounce apart, depends entirely on all of the details of the collision. This is really the conceptual way to think about momentum, and then later on in this video, we're going to use this equation. This is our bread and butter conservation of linear momentum equation. It should be in your notes. If not, take a moment, pause, make sure you do have that in front of you. So when we talk about collisions, we want to talk about elastic and inelastic collisions. I'm going to show you an example of what would be like a 50% elastic collision. So I'll play that again. You can see that marble bounces. I dropped it from 1 meter and it bounced up to right around 50 centimeters high. That's about a 50% elastic collision. If it bounced all the way back up to the top, we would say it is 100% elastic or perfectly elastic. Over here we have a nearly inelastic collision. You can see it hits the ground, makes a terrible thud noise, and maybe bounces a centimeter, maybe 3 centimeters maximum. So this first one's about 50%, and this one, essentially all of the energy is lost. Where does that energy go? We're going to talk about that. So, quick definitions of those terms that I just showed you in the last slide. A perfectly elastic collision, the total kinetic energy before the collision would be exactly equal to the total kinetic energy afterwards. Now, this is an idealized situation. It basically doesn't happen in the real world, though we will see questions like this where things are perfectly elastic, or collisions are. It's basically impossible in real life, and we'll talk about why in just a moment. On top of that, we've got perfectly inelastic collisions. That would be one where all of the kinetic energy is completely lost during the collision, which is very, very nearly what we saw in this one. It had 100% of kinetic energy up at the top, and when it hits the ground, it basically has none. Maybe it had 1 or 2% of the energy left. So that's why I said it was a nearly completely inelastic collision. So, in other words, whereas in a completely elastic collision, the energy before, kinetic energy before, is exactly equal to the kinetic energy after. But in a perfectly inelastic collision, those two values will not be equal. So for example, let's say we have a perfectly elastic collision. We have 100 joules before, 100 joules after of kinetic energy. That will not be the case in a perfectly inelastic collision. In fact, if it's a perfectly inelastic collision, the total kinetic energy after will be exactly 0. In other words, all of the objects will stop. Now, we'll talk about more later how it's possible for the kinetic energy to be lost and the momentum to still be conserved, because it's always, always, always conserved in every collision. I'll move my little head there. Real collisions, though, are somewhere in between. Every real collision is going to lose some kinetic energy during the collision, so they are partially elastic, or you could say they are partially inelastic. It's kind of up to you, and we'll look at exactly what I mean by that in just a moment. So, let me show you an example of a real collision. I'm not going to show the whole video, but here we have a person serving a tennis ball. And what you're going to see, it's just going to play it through once, and then it's going to go slow-mo, and we'll talk about what we're seeing. Whoa. So, the question is, in a real collision, where does that energy go? If some of it disappears, conservation of energy says there has to be some energy. Well, it turns out a lot of it is to do with the squishing of the ball, which we can see happening right here. that kinetic energy is being converted into the heat energy of the tennis ball. It's also being converted into the elastic potential energy that is required to actually squish the ball. You can think of the ball as being like a weird yellow round spring. So that's where a lot of the energy is going. In fact, this is such a good idea. This is such an important concept that in a moment we'll talk about how this actually can save lives in car crashes. So back to our example, this is both of those videos with the ball put together. We've got our inelastic and our elastic drops. Most, again, of the energy is going to squishing, or that word there, deformation, the ball squishing. And then also you heard that thudding sound. A lot of the energy is actually going to sound. You can hear it bouncing and losing energy each time. That's where a lot of the energy is going, to deformation and sound as well. So which of the happy and sad balls squishes more during the collision? Well, since the sad ball doesn't bounce very high, it's likely that it squishes more. If we could get really close with a slow-mo camera, we would likely see it squish quite a bit more. So I'm just going to play the first bit of this video, these two cars crashing. We may discuss this more during class time. This is a crash between a 1959 Chevy Bel Air and a 2009 Chevy Malibu. The big difference between those is a number of safety features which are enumerated in this video. Well, perhaps the biggest one that we want to focus on here are the idea of crumple zones. Crumple zones are an intentionally weaker material that's meant to bend, crack, and buckle. And we'll see why it is meant to do that in a moment. The big idea is that we're trying to convert as much of the kinetic energy of the collision into the elastic potential energy of squishing a car. So again, I'm just going to play a short bit of this video. You can find this video online, and there's actually a pretty good narration over the top of it. So we'll just see the crash and then we'll move forward. Oops. So here's a GIF of that same thing occurring with sort of an X-ray look at the car, and instead of two cars colliding, you're just seeing one. So the idea here is that it's squishing, and really we can use impulse to understand why you'd want a crumple zone in your car. Early, when people were designing cars, in the 1950s, you thought, oh, I want a strong material. I want it to be made out of the toughest steel possible. But I want to try to show you why that's actually a terrible idea. So think about it. Your car is coming in. It's got some fixed velocity. Let's say it's 50 miles per hour or whatever, 75 kilometers per hour, something like that. And you can't really change the mass. That means that the momentum is fixed. You can't change the change in momentum. The car is going to have some momentum before it hits, and then it's going to be stopped after the collision. So we can't change the change in momentum. What we can change is the total time it takes for the car to squish. Since the force times the time is still going to be multiplied to equal the same number, the time with a crumple zone is going to go up because it's going to take longer for the car to come to a stop because it's squishy. And that means that when we multiply them together, that means the force has to go down to equal the same change in momentum. If we want the same change in momentum, that means we're going to have a tiny, tiny force because the change in time got much, much bigger. Also, I won't show it here, but I've linked to something like a 10-minute video all about a person doing a home experiment on the Tesla Cybertruck design. It's definitely worth checking out, definitely worth your time. Just wanted to take a moment. You might be wondering, we've talked about some elastic and inelastic collisions, but I mentioned that no actual collision in real life is perfectly elastic. The only one that I can really think of happens at the subatomic particle level. Here you're actually seeing what's called a Feynman diagram, really interesting subject, of two electrons. This electron goes in, this electron goes in, they exchange a virtual photon. What? And then they bounce apart. This is the same as saying that electrons repel one another. I'm not going to get into the details of that. You don't even need to know that. I just think it's kind of interesting. While we're on a little bit of a tangent there, if you're curious, what do modern physicists do? Well, this is the kind of thing that they look at. They build enormous 27-kilometer wide particle accelerators where they collide 1 billion protons every single second to conduct their experiment. And they can get them to speeds 0.9999999 c, or to put that in context, just about 3 meters per second short of going the speed of light. So these things are going super fast. In fact, one of those protons has about the same kinetic energy as a fastball in Major League Baseball. What they do is study these Feynman diagrams, and in fact, I'll move my little picture over here. Back in 2012, they announced that they had discovered something that had been hypothesized back in the 1950s, and then from the 1950s until 2012, people had built bigger and bigger and bigger particle accelerators. In a roundabout way, they helped invent the internet to get all of this data managed, and finally discovered the Higgs boson, which is sometimes referred to as the God particle. Again, confusingly here, it actually grants mass to matter. So we have matter and we exist because of this thing called the Higgs field and the Higgs boson. These things in red here in our Feynman diagrams are a consequence of the Higgs field existing. It's all very important to physicists and our understanding of the modern world. So if you think that this is really interesting, in addition to all the great stuff we're doing with car crashes and collisions, you should consider studying physics, because this is one of my most favorite areas of physics. Modern physics, particle physics is what we're speaking about here. Anyway, so let's try a couple of experiments. We're actually going to show some data that I collected, and we'll do a calculation here in just a moment together. So this is a classic hit and stick style collision. So I actually have some Velcro attached to the front of these carts. I'm going to show you what that's going to look like. Unsurprisingly, when I pushed the carts, they hit and stuck together. This is a position versus time graph of that same thing, just a screen recording of my computer while I did it. So you can see the yellow cart was sitting in the middle and was greeted by the green cart. Then they hit and stuck together somewhere in the middle. What's really important, this is the conceptual thing that we're going to focus on while we solve this little experiment, is the total momentum before the collision should be exactly equal to the total momentum after. And the other question we want to answer is this an elastic or inelastic collision, and just how inelastic was it? So with that in mind, here's the experiment that we are going to try to conduct. First, we're going to show that the momentum was conserved within reason. Keep in mind there's going to be little bits of error here and there. But we want to try to show that the momentum was conserved during the collision. I'm going to show you how to do that in just a moment. And then the second thing we want to do is calculate how elastic that collision was. So to find out how elastic it was, we just take the total energy, kinetic energy, after the collision and divide it by the total kinetic energy before the collision. You can leave that as a fraction or as a percent. I've also included here the masses of the carts. Now what I'm going to do is pause and get out a piece of paper. We're going to also show you some of the real data that was collected, and we're going to try to do both parts of this experiment.